In this session, we will learn about doing descriptive statistics and also regression analysis in Python using the pandas and the stats model packages. In this presentation, I'm going to assume that the concepts and the theory behind statistics and regression analysis is something that you've looked at in other courses, such as the basic statistics course. What I'm going to do, I'm going to show you how those techniques are available in Python. We're going to start with descriptive statistics. So first, I'm going to import the pandas package because I'm going to use it, and I'm going to read this data file called diabetes.csv from the data folder here. The pd.readCSV function is going to read and parse the file into a data frame. So I have assigned this data frame to the variable data, and then I'm doing .head to show the first 5 entries, the first 5 rows in this data frame. So as we see here, this file contains, or the CSV file contains a couple of columns, such as pregnancy, glucose, blood pressure, skin thickness, insulin, BMI, and so on and so forth. The main important variable in this data set is outcome, which is whether the patient is diabetic or not. And there are a couple of predictors that are used to determine this outcome. We're not going to do a regression analysis on this data set today. Rather, we're going to start just looking at this data set and trying to gain a better understanding of it. So the very first step we want to do in any exploratory data analysis is to look at the descriptive statistics of all of the variables. The descriptive statistics include measurements that summarize the variables. Those measurements include, basic measurements of central tendencies, such as the average or mean, count, for example, and measurements of variance, such as variance and standard deviation, and so on and so forth. The function describe is a very handy function because this function basically reports the main important descriptive measurements for all of the variable in the dataset. And this function will operate only on numerical variables, which is the case in this data frame. If the data frame had any categorical variable, it's going to be dropped when we do describe. So if I do data.describe, I'm going basically to see another data frame, but this data frame doesn't contain the data. It actually contains the descriptive statistics for each one of the columns. Right, so we see the count, we see the mean, standard deviation, the minimum, the first quartile, the median, the third quartile, and the maximum. So, once again, you've probably seen those measurements in, statistics course. I just want to comment on the count because that's kind of seems straightforward, and why would you want to report it in all of these variables? In this data set, we don't have any missing values. If there were missing values, then the count is going to ignore these missing values, and hence the count of entries records per variable may differ. Say, for example, glucose column, there were some missing values. Those are going to reduce the count here. What's important in here is that each one of those descriptive measurements is actually available as an aggregation function. The name aggregation implies that we are aggregating the whole data into one single point. For example, if I do data.mean, I'm going to calculate the mean for each one of these variables or the columns in the data frame. Now, furthermore, I can actually calculate this on a specific variable. If I want to select a specific variable from a data frame, a specific column, I can use the index notation, which is the square bracket in this case, and I can put inside it the title or the name of that column, such as data pregnancies. In this case, this is going to give us a column containing the numbers from the data frame. And I can call the function describe on this column here. And this is going to give us the descriptive statistics for only this one column, right? And that's basically the numbers we've seen here. So this is kind of more specific. If we don't care about all of the variables, we only care about one particular variable, you can use this syntax. We can actually call the aggregation function. So if I'm only interested in the mean of data pregnancies, I can do data pregnancies.mean, and this is going to give me the average pregnancies in this data frame. Okay, so that's about the descriptive statistics. Another very useful exploratory analysis tip is to look for correlations in between pairs of variables. So remember the concept of correlation. It's basically a coefficient that varies between -1 and 1. 0 being that the two variables are not related at all, or not linearly related, to be very specific. 1, it means they're perfectly correlated. It means when the first variable increases, the second one will increase. -1, it's kind of the opposite. It means when the first variable increases, the second variable decreases. So if we do the correlation matrix, the syntax is to use the function CORR for correlation, and this function will produce the correlation matrix for pairs of variables. So this matrix is symmetrical here, and the value in this cell indicates the correlation between the two variables, for example, pregnancies and glucose. And we see here 0.12 or 12% correlation. And those two pairs of correlation are useful to detect variables that go together or go against each other. For example, let's say I am interested in outcome here. So it looks like whether a person is diabetic is correlated with pregnancy's glucose. It's actually correlated with blood pressure, but not so much. It seems that glucose so far is the variable which is most correlated with outcome. Looking at the remaining of them, so we can see age, right, BMI, and the other variables are correlated, but not as much as glucose, BMI, and age, right, 46, 29, and 23%. So that kind of gives us an idea of the relationships among the variables in this data set. Now, by default, the correlation function produces the Pearson correlation coefficients. It's possible to report other kinds of correlations, such as Spearman correlation or Kendall correlation. Once again, the differences, the theoretical differences among these correlation measurements is something you need to go back to a statistics reference to learn about, or you can search for these differences. Spearman is very useful if you're not looking for linear correlations and you're looking for rank correlations among the variables. Here, for example, if you take a look at, let's run this for Spearman. If we take a look at outcome, you can see that it's still highly correlated with glucose, BMI, age, for example, and the numbers are very similar to the Pearson one, which tells us that not only those variables are correlated, but the relationship is more or less linear. So that summarizes doing descriptive statistics with pandas. We need a data frame, and the two main useful functions is the describe function and the correlation function to produce the descriptive statistics and the correlation matrix. Next, we're going to take a look at regression analysis. Regression analysis is basically a statistical modeling technique where we are interested in an outcome and we are interested in explaining this outcome as a linear combination of other predictors, hence the name linear regression. So basically, we want to extract this model of this relationship as a combination of the predictor. So we want to say, for example, that our outcome y is a combination of the predictors x1, x2, and x3. And the linear regression model is going to tell us exactly what the combination is. So it could be, for example, 2.5 times x1 plus 3 times x2 minus 1.5 times x3, and so on and so forth. So this technique is very useful for modeling relationships in a data set, and specifically relationships that link a couple of predictors to one outcome. There are many caveats to regression analysis, and today we're going to look at the basic linear regression, or what is referred to as ordinary least square or OLS regression analysis. However, many of the variants of the basic regression analysis model, if you've looked into some of the variants, for example, such as logistic regression, for example, are available in the same package, which is the package stats models. So the package stats models provides a couple of statistical modeling techniques in Python. What's very useful in this package is that it uses the same syntax that the R statistical package uses. That basically means that what you learn in Python using stats model can be easily applicable in R, and vice versa. If you learned how to do statistical analysis using the R formula syntax, it's very easy to kind of port your code or your analysis into Python. So we're going to take a look at the basics here, and I have linked to the full tutorial from this notebook. All right, so the very first thing we need to do is to import the stats model package, and we're going to specifically import the API sub package, and we're going to give it an alias SM. So instead of typing every time stats model.api, we're going to use SM. We're going to import pandas, and we're going also to import the library the sub package G matrices from Patsy. This one is not important unless you want to really go into the details. This is the main important package that we need to import for being able to use stats models. In what follows, we're going to use a dataset which comes built into stats models. This dataset is called the Gary dataset. And this dataset is about demographics from France. The main important, and I have linked to this data set here, so you can take a look at the further details about what's inside this data set. Basically, we have information about different states in France, which is called DIP or department here, and the regions of these departments. And then we have demographics information such as the crime, again, population crimes against persons, or population crime against property, literacy rate, donation infants, and so on and so forth. So we're going to load this dataset here, and this dataset I'm not going to use read CSV because this dataset comes comes with stats model, so I'm going to import it using the function here, get our dataset. Okay, so we're not going to look at the whole data set. We're going to simplify things a bit. Um, for now, I'm going to focus on these following columns, variables: department, lottery, literacy, wealth, and region. So remember the discussion above when we wanted to look, let's actually do head here. So head is going to give us the first 5 rows in this data frame. And you can see that we've got many columns here, 23 columns. Now, remember the discussion from a few minutes ago. If we want to extract one column from a data frame, we can use this index notation. And so we can do df square bracket region, and that's going to give us one column. Now it happens that the same syntax applies if I want to extract multiple columns. So if I want to extract, for example, region and department, what I can do, I can tell pandas that, hey, I want not only one column, I want 2 columns. So I'm giving it a list of columns. For example, region and department. So this technique is called fancy indexing. And basically, you're providing a list of the columns that you want to extract. uh, to the index operator, and hence we have to have two square brackets here, one for the indexing and one for the list of the columns. That's going to give us a subdata frame. And that's what we are doing here. What we are doing here, we are selecting few columns: departments, lottery, literacy, wealth, and region. And let's just focus on those variables for now. This notation -1 to the end basically means show me the last five the last five rows from the data. And actually there is a function called tail that does exactly the same. Okay. So now we notice here that we've got a null value, and this null value is going to cause us some issues when we are building a regression model from this data. So to deal with these null values, I'm going to drop all of the rows containing null values from my data set. So I'm going to do df.drop na, assign it back to df, and now we don't have any null value here. All right, so let's kind of take a look at the analysis here. In this analysis, we're going to try to predict a variable called lottery as a linear combination of the variables literacy, wealth, and region. Now, just as a backdrop explanation here, and this is the historical data set about France under the old regime, under the royal regime. And lottery was a way to taxing the population. But instead of taxing the population based on a deterministic formula, they decided to run a lottery to tax the population. So this was kind of a maneuver from the king, basically to avoid imposing a tax on the population and kind of frame it as kind of luck. In this case, it's kind of a misluck of a certain department of being taxed. It's an interesting concept in here. However, we want to kind of see here if indeed the lottery was as random as it was supposed to be. And we're going to do this by linking the lottery, the outcome, to other predictors such as literacy, wealth, and region. So one way to do this linkages in here is to use the function day matrices, and D matrices will take this syntax, which is very similar to the syntax that our regression syntax uses. And that basically is going to give us two things. It's going to give us the target or the outcome y, which is lottery in this case, and it's going to also give us the x, which is the predictors. Now, one question here is that, like, why do we need to do this? We could have done this using the square bracket notation as we've seen. And the answer is that this does something more than just extracting columns from the data frame. As you see here, region used to be one categorical variable. And instead, we've got 4 columns for region. And those are dummy variables. The reason we get those dummy variable is that regression analysis, very much like many statistical models, do not operate on categorical variables. They only operate on numerical variables, and hence you need to convert a numerical variable, categorical variable to numerical variables. One way to do this conversion is to create what we call dummy variables. So for each value, and we've got 4 values, east, north, south, and west, we're going to get 4 variables. So basically the first observation in data, let's do data.head here, was an observation, sorry, not data, gf, was an observation from the east. Hence we've got 1 for the east, 0, 0, 0 for north, south, and west. Similarly here, the second one is north, so we get 1, and the rest are zeros. So it's a standard way for converting categorical variables into numerical variables for the purpose of doing regression analysis. Once we do this, we can pass in the y and the x to the function OLS from the stats model package. So here we're saying that we want to use the standard ordinary least square model. That's the first step. We describe the model. The second step is to call the fit function to fit the model to the data and estimate the model parameters. Once we estimate the model parameters, we can look at those parameters, and one way to look at everything in kind of a holistic view is to use the function summary, and that's going to give us a overall summary of the model. Once again, I'm not going to kind of talk about the theories behind everything we see in here. I'm assuming that this is something you've learned in statistics, and I'm going to quickly walk through it. All right, so we have some basic information here, number of observations, degrees of freedom of the residuals and the model, the covariance type for the standard errors, and then the R-square and the adjusted R-squares, and that's the model goodness of fit. So 0.33 means 33%. That's basically saying that the model explains, roughly speaking, 33% of the variance in the outcome variable, which is lottery. We've got also the F statistics and the probability of the F statistics under the null, which is F statistics is significant. Here it's significant, so the model is significant. And then we've got other measurements such as for the model fitness, such as the log likelihood, AIC, and BIC. Next, we get the coefficients, right? Remember, this is a linear regression model, meaning the outcome, which is lottery, is linearly related to those coefficients. So here we are saying that lottery equals 38 minus 15 times that variable, region east, minus 10 times region north, minus 4 times region south, minus 10 times region west, and minus 0.18 times literacy, plus 0.4 times wealth. What we also get here, we get the standard error of the coefficient, how that coefficient is supposed to vary, and also the t-statistics. Testing the null hypothesis that this coefficient is equal to 0. Although we see the value 38, there is some variance around 38. And here the variance, if you look at the standard error, is kind of big, and the t-statistic serves to show whether this is the null hypothesis, which is the coefficient equals to 0, is statistically significant or not. And we can see that here with a probability more than t, that's a two-tailed test, which is 0. In this case, it means that this is highly significant, which means the intercept is highly significant. So on average, the holding everything equal, the king is leveraging. Let's take a look at the variable here. That's the per capita wager on Royal Lottery, 38, whatever the ranked ratio of the proceeds bet on the Royal Lottery to population. However, if you look at the remaining coefficients and you take a look at the t-statistics and also the p-values here, you can see that all of them are greater than 0.10. Usually we use the value 0.05 or 5% as a roughly cut point for deeming a coefficient to be statistically significant or not. And more recently, there is a recent trend to even use smaller values, such as 0.01. Anyhow, in all of these coefficients are highly insignificant because all of them are greater than 10%, which basically means there is no statistical difference among the regions. It doesn't seem that the lottery is targeting a specific region in this case. If you take a look at literacy, although if you look at the coefficient, it's negative. It means the more literate the region is, um, the less kind of the leverage on of the lottery on the region. That relationship is statistically insignificant as well. The only other statistically significant variable is wealth, which is really interesting in this context because you see that wealth is related to more taxation via lottery in this case, 0.4 on average. So if you take a look at the wealth variable here, let's search for wealth. That's kind of corresponds to the per capita tax on personal property. And it's interesting that it's also related to this lottery tax, which kind of gives an indication that although it's framed as a lottery, it's perhaps was targeted to wealthy uh, individuals. The other explanation is that maybe it was not targeting individuals, but probably it happened that wealthy individual ended up paying the tax versus, poor individuals who were kind of unlucky to be selected, but anyhow didn't have the capacity to pay the tax. That actually requires us checking the context and from which the data was collected. Anyhow, from a statistical perspective, we've got the coefficients here, which serve to relate the variables, the predictors to the outcome, and we've got the model fitness test here. And we have some more information here about the model that I'm not going to get into. We can actually inquire about these results individually rather than printing all of them. And the way to do it is to access them using the dot notation. So result dot, and if you hit tab, you're going to invoke code completion. And that allows you to pick specific model results. For example, if you only care about parameters here, you can do, you can do parameters. You can search for parameters or params, and that's going to give you the model parameters. If you only care about r squared, you can do result.r squared, and that's going to give you the r squared. In addition to the basic results, stats model also allows you to do a range of useful regression diagnostics and specification tests. So those tests are important if you want to kind of show that your linear regression model is a good model given the dataset, since not all datasets exhibit linear relationships. So for example, you can do the linear rainbow test, in which the null hypothesis is the relationship is linear. And in this case, we don't fail, we don't reject this null hypothesis, which means it's roughly speaking, um, valid linear in this case. We can actually do plots to show some of those relationships under the regression. So we can do a partial regression plot using the function partial regression. And this function is going to show the relationship between two pairs of variables that we specify, such as, in this case, the outcome lottery and wealth and region, holding things, other things constant in this case. So we're going to see more of these plots when we talk about visualizations in 2 sessions. This summarizes the discussion of descriptive statistics and linear regression analysis using Python, and we have 2 exercises that are going to build on this discussion.